just to say this work is really it's kind of work in progress, but we'll see as we go along that it builds on some techniques that were kind of developed quite a few years ago. I wouldn't say maybe 30, 25 years ago. So let's get started. And the whole idea here is to get towards some kind of effective memory management, and effective in the sense that it should be a little bit easy for the programmer to specify and control memory effects. So there's been a lot of work on reasoning about effects in higher order programs, effect handlers and whatnot, and type and effect systems that this work is built on. And some of the questions you ask is, of course, does a program make good use of memory? And maybe parallel threads, do they execute without allocation and mutation races? Are there unhandled exceptions? Can a function mutate shared resources? All of these things. And there have been developed many solutions to solving some of these problems. But the goal here is to provide some predictable behavior and control with only few programmer annotations in the program. And it should also be scaling. That's some of the goals, that we should have some modular scaling facilities that you can actually deal with large programs and deal with a rich set of data types and functional capabilities. So I will just say a little bit about region-based memory management and region inference. So you guys can see also here. There's this idea of explicit region-based memory management, where the programmer will associate the lifetimes of objects with the regions, and then reason about how and so on these regions are allocated and deallocated. And examples are, of course, Cyclone and Rust. And then there's this notion of region inference, which in principle just takes a non-annotated program, and then it will do its best to annotate the program inside an internal representation, and then it will use those annotations, and hopefully it will find a sound way of annotating the program, so that a backend can really generate code that will use regions as the underlying memory management strategy. So here we have the traditional work on regions, where you have a stack of regions. So the stack can grow, but each region can also grow independently of the other regions while the program executes. This machinery then has been incorporated in a compiler for standard ML. I'll come back to that. And then ReML is this language built on top of standard ML, which will allow the programmer to make some annotations. But it's also the case that an ordinary standard ML program is also a ReML program. So you can kind of start with very few annotations or no annotations at all. Everything will be based on region inference. And then the idea is that you can start having the programmer annotate and then control and get guarantees about memory. So we have this notion, we call it gradual support, even though there's no kind of runtime things going on here. So the gradual part is mostly that you can you can basically choose where you put your annotations, and then the inference will do its best, and the inference will also, the annotations will be respected by the underlying type system. So for expressions, for instance, you can say that you're allocating a pair 4 and 5 in the region R. So you have this backping annotation there with the regions. And you may also annotate types with regions where you basically, there's another way of saying that the pair 4, 5 should reside in region R by specifying a type, a region annotated type that basically says that kind of constrain the value to be stored exactly in that region R. And then you have this effect scoping where you allow, and we use width as the keyword here instead of region, but width is a keyword in standard ML, so it was a trick to kind of get a new way of actually having backwards compatibility. So we can have these width declarations where you basically specify a region, and that specifies the scope for that region. And then you can also define functions that take regions as parameters, and so on. Function declarations may also be annotated with these contractual effect constraints, which may be used to say things like that two sets of effects should be disjoint. That might be a good thing for executing two different expressions in parallel, and then you know that there will be no allocation races between the two functions when executed in parallel. And this ReML then is built on top of the ML kit, which is a compiler that has been implementing with primarily just with region and effect inference. So the new thing in ReML here is that you can provide these user annotations.
So is the width actually allocating a region, or is it declaring a region variable?
It's basically lots of analysis going on, which might define that this region there will only ever be one value being stored into it, so it's allocated on the stack. So there will be space on the stack to be.
It's a hint to your existing region inference algorithm.
Basically. It's a hint, but it's also a contractual constraint, so to speak, that if some value is not respecting that scope, right, then you get an error.
Right. Yeah. So it means there has to be some region.
So there has to be some region that, and you might use that R in some allocation specification and so on. And if the region type system will not be satisfied, then you get them.
Yeah.
So let's just go back a little bit with the region inference stuff. I'm sorry for giving you a little bit of background before I get into the new stuff, but region inference is really this idea that you take a source language, the lambda calculus with letreg expressions, and then you have these possible annotations as explained here with row and end, and you can every allocating expression is then also annotated with the region in which this value should be stored. And you then have these inference systems that will allow you to generate a new expression E prime, and is a type and effect system, so it will also carry an effect, and you have an enriched type system, a system of types, where types also have effects on the arrows. So here's a simple example of the region inference in action, where the inference algorithm has figured out that there are some local regions, row 1 and row 2, and then there are some then there's a more global region row here, which will survive the execution of the program and store the value of y. So here we have a local pair being created in row 2. We also have a value here, which is created in row 1. Then we project the second component here, which is this real in here. And then the two regions allocated, row 1 and row 2, they will go out of scope, being deallocated, and then only row is surviving, and the value in row. So that means that the region inference can maintain this idea of having local memory, and it will be type safe and so on. There are lots of issues here, and with higher order functions and things like that, you can get so-called dangling pointers that will refer to some some values which will never be used in the remainder of the computation, but it can be shown that they will never be accessed, and that means that region inference can actually get rid of that memory, even though a tracing garbage collector will not be able to deallocate those things.
Martin, if you had one of these grid blocks, if you return the closure, actually some data that's stored in that region, that would be a type error.
There will be a type error, but only if that effect in that closure will be executed at some point later on, right? So if the closure is not called for some reason, the effect will not appear, and then you might actually have leaking closures can be fine, but it has to be a little bit more. They have to appear as free variable in another closure to see that example, because otherwise they will appear in the type of the closure you are returning, and then you will basically not be deallocated. So you can get some advanced cases where you will have these dangling pointers. So here's some support in ReML where you can be explicit here. Example, again, you allocate something, you project, and you also have a notion of global regions where you're allocating something in a global region and you don't have a width construct. So you have some kind of built-in global regions that you can use for various cases. And of course, a sound annotation of your program will just be to store everything in global regions and have no width constructs at all. And that's actually also a sound way of region inference. That can be the choices it does, because that would not be good choices, because then everything will just live without being garbage collected. So region inference is about finding a best program, so to speak, that somehow will deallocate as much as possible during execution. Yeah, that's because, and why is it called R0 pair? That's because the underlying mechanism here is doing a lot of things to try to get untagged and untagged representation of pairs, for instance, where the pairs are really just stored as two words, not with a tag header and so on. And that means that the R0 pair is a region in which that tag is stored with the region and not with the values themselves. So that means that there are some specifics, and this is one of the things that we would like to kind of get away. This is actually a good question, because this is really, for the programmer, this is not too nice, of course, to be able to have to specify it like this. But until now, we have been kind of limited that we have to respect the underlying implementation of how pairs are implemented and so on to deal with this. But this is actually one of the key points here is that in this talk that we would like to have a more abstract notion of what a region is than just the specific ones that are implemented for the sake of performance and so on. But you need to wait for the programmer to actually have the possibility of working in a more abstract way. So here are some examples of a function that will take a region as an argument, and then will return a list in that region. And here we see that the list type constructor is an integer list, and then that list is stored in region R. In fact, the pairs that makes up the list, they will be stored in the region R. And then we can call the function, and we can kind of extract the first element, and then again deallocate the list. Here's an example of a so-called region exomorphic function, one that will take an argument in one region, and then it will possibly return a value in another region. It might return a value in the same region. That depends on the call side and how the function is instantiated. But it does allow for the call side to specify two different regions for the parameter and the result. and that's the copy function here. And of course, if we're not copying the tail of the list, then of course the type inference system will enforce that the two values will that the returned value will be stored in the same region as the argument. And if we don't, if we forget to put the copy there, then the implementation, the type system will complain with a type error that you cannot unify these two explicit region variables. So this is one of the features that you gain from programming with the system. Here's another example of something called an endomorphic function that will really return a value which is stored in the same region as one of the arguments, and not in a fresh region, so to speak. So here we see that we are appending. This is the usual append function, and that will of course share the right argument and cons all the left argument elements onto that onto the second one and return that new thing. But that will be, since we are now having sharing between ys and the result of the function, then that those two things will have to live in the same region. Of course, we can explicitly copy ys first and then call append, and then we can write our own thing that will really deeply copy the entire list instead, and then turning that one into an exomorphic function instead. Okay, so how do we actually program in the large with such a system? So we saw some very small examples. It has been used to enforce these things, as I talked about, mentioned earlier, the notion that the effects of two functions should be disjoint. That will allow for reasoning about absence of allocation races, and this notion of effect constraints can be used for these things that are built in. I'm not going to talk more about effect constraints here. And then there are also examples. Region inference support this notion of polymorphic recursion in regions, not in the types, but in regions, that allow different call sites within a recursive function to use local regions for those local calls. And that will allow for instance, things like a merge sort to behave efficiently and deallocate the temporary sorted lists, for instance, and deallocate those after you have performed the merge operation in a merge sort. But it's very fine-grained, as we also saw. We needed to annotate precisely what regions things are allocated into. How do we actually allow for programming with some larger structures? So this idea that we will introduce here comes all the way back from this paper, and that was in the FEST script for Robin Milner. It's from Lars Birkedal and Mads Tofte wrote this paper on contractions, which is basically defining the fundamental toolbox for defining unifiers for types in terms of substitutions. So with these effect sets. So the problem is that once you start having effect sets in types, effect sets on the arrows and types, what would be a unifier for unifying two types with such effect sets locally inside? How do we actually find a substitution that will make them equal? This is a notion of contractions that they came up with, and really you're then trying to unify these effect graphs. And there's a kind of a mathematical definition of all these things under what circumstances they are well defined. And this also goes a little bit into the notion of region inference itself, the termination proof that the inference will terminate. And that termination is based on the idea that first you will create a lot of fresh region and effect variables and spread them all over the program. And then you'll start you kind of want to make sure that the typing rules are satisfied, also in particular for the end resulting expressions, that the typing rule can be satisfied. And various places in the typing rules, you will have to unify in function applications, for instance, you need to unify types. It's really Milner's algorithm W that comes into play here. So you have these unifiers, and these are the contractions. So after you have spread fresh region and effects all over the place, you start contract the program and all the regions and effects in there, and you still get something that looks like effects. So that's the whole theory that they developed there, the notion of contractions, that are these substitutions that will make sure that at the end, you can only contract, only making things smaller, and at the end you have in the very worst case, you will have just one region, the global region, and the program will just use that one region in the worst case. But of course, it will try to do something better than that, and there's a notion of principality in unifiers and so on, that you can find the best contraction that will unify these two types. And now the idea here is then that we can try to use these contractions to make programmers specify more, so to speak, high-level types for functions. So here's an example of a compiler, and this is where it's work in progress. So this is not fully implemented. There's some way to it, and there's also some work on actually defining the underlying properties that we will need. But let's look at an example of where such a thing could be a very nice thing to have. We're assuming a larger program here, trying to write a small compiler for a functional language, and we have some compilation passes. The first one will parse and type check a file, and then we'll return some AST data structure, abstract syntax tree, in some region R. Of course, underneath it will really be in many regions. This data type will usually, after region inference has played its trick, it will be maybe in 8 or 20 regions, depending on the size of the language. So what we want to specify here is that there's just one region. We'll just call it R, and the AST is residing in that one. And also there should also be some compiler from AST to IR that will take an AST value, and then it's exomorphic. It will return a new thing and a new internal representation, IR, and store that in region R2. And notice that we have this idea that R1 and R2 should be disjoint, in the sense that if you can write the function like this, you can pass in and specify that R1 and R2 are the same, but you can also call it in a context where they are really different. So you know it's exomorphic, this one. Optimize, on the other hand, will try to take some IR representation, will do its best to optimize it, but it might also just return, just be the identity function, or in some cases it can't do anymore. It will just return the argument. Then there's a compiler from an internal representation to assembler again. We are here assuming this is exomorphic. And that can be checked that this function indeed has that type. And we can then finally emit the thing, the code here. So let's then see how it's usually you would write the compiler function from start to finish here. You have a compiler will take a file input and a file output, and then it will parse and type the file, and it will compile it into an AST. It will return an IR, and then it will optimize the IR, and then it will generate assembler code and then emit it. Now, region inference will do good on this stuff, but it will not have the optimal memory behavior as you could if you kind of allowed for a little bit of lead floating in your program. So you can rewrite the program so that the AST is not alive after it has been compiled into an AST. Right? The memory that will be set aside for the AST can be thrown away once we have the IR value. And this is what the program to the right. Here we have done the lead floating, and then we have also specified explicitly the regions into which the different into which the different ASTs and IR values will be stored. But we're not being explicit only at these kind of virtual regions and not at the specific ones. And this will have a much improved memory behavior, of course, compared to the original. The problem here is this thing with that in reality there will be many more regions, and we need to find a way to kind of allow many regions to kind of be allocated in one virtual region. And this is where this notion of contraction comes in, because these contractions kind of can make the can kind of map each of the regions into a particular one region. So, for instance, the ASD, if it has kind of 3 local tuples in the ASD, for instance, they will be allocated in different regions, R1, R2, or 3. But with these contractions, we can kind of make them look like they are allocated only in one region. And that means that we can have this annotation ASTR that will basically just say that the same region here, or maybe the same region of different kinds. We have the pair regions that are specific and so on, but they can actually be grouped together so that we have a much simpler system to work with from the programmer's perspective.
So this regionality is inferred by the compiler, or is it the user that is very?
It's inferred by the compiler, and what it does is it looks at a data type definition, and then it will basically see there's a constructor that takes a tuple with 5 elements, there's one that takes one with 3 elements, there's one that takes 2 closures, and so on. So it will try to define the arity, and that means that the auxiliary regions in which a value of that data type is stored is basically given explicitly. So you can imagine then that if you have a full program, there will be a lot of regions around to read, this is this and this is that, and so on. But of course, from a programmer's perspective, you really want to collapse those things into one chunk of values and reason about it at that level, unless you need to go deeper. So you want to be flexible with respect to that.
Follow up on that. It's just basically on that this sort of region where it's a different layer. But some sort of like within one of these arguments is the case.
Yeah, that could definitely be the case that they are set aside, allocated. Usually you can also collapse them somehow, but they will be set aside, and not if it's not used, then it's not. Then it will just be an empty region. Yeah.
Okay, like I'm like
yeah. So just to end up here, we are looking at this. We have all these things with the consistency of region and effect annotations. We're still doing this, and this is ongoing work with the leading contraction after checking is memory safe. And the idea there is that once you have the user annotations, the type system will be satisfied also with these contracted regions. We would like a proof that you can actually not implement it like that. We would actually like to just throw away all the contractions and then use the underlying regions that were inferred for the back end of the compiler, because that will be much more efficient and maybe even better. There are examples where you could have better memory management than being with the explicit one. But we still need a proof for that if you have a contracted system, a contracted program, then when throwing away the contraction, still having a region annotated program, that program will work as efficiently as the contracted one. So this is some ongoing work, and it will require some small steps, store-based semantics, to have a relation between the contracted and non-contracted setting, and be able to talk about what it consumes the most memory. And it also needs to be small steps, since we need to have it maintained all throughout.
Martin, what do you mean by efficient?
And efficient in the sense that we are not allocating more memory in one case than the other.
So your design is based on trying to minimize the amount of memory
At least making sure that you're not kind of drastically increasing the amount of memory used.
Someone who likes automatic memory management, like one of the key things of automatic memory management is that sometimes throw memory at the program to make it go faster. Like what was the story here for doing something like that?
That's a good point, and maybe that could lead to two different kind of annotations. If you're really in that situation, maybe you want to kind of enforce something. But also from here, we are just from a semantics point of view, or is it really sound to just throw it away? Yeah, this is the first thing, and I think there could be, of course, more ad hoc choices where does it make sense or not, and so on. But is it really sound just to throw it away? That's kind of the open questions that we're trying to answer. Yes, mostly here we are concerned about control. Yeah. Making sure that if somebody else does an update to the program, you still have the things that you typed in. I mean, you still have the properties, right? Where we read in inference, you have to analyze the intermediate expressions again. Does it behave as I did last time? Somebody did some change to some function, forgot a copy somewhere, and suddenly the whole execution will explode in memory. Here we can be explicit and make sure that that invariant.
Something I guess about earlier, which is companions. Oh, I think you were originally thought I was just ideally, if I don't without having if they have to be the same age, I remember that.
There are different in some aspects of readings that are dynamic, that are more kind of, I don't know if that's where you were heading. Well, we do have a check. Is this the same pointer? But of course,
Is this something yeah, I mean, the general question because it's the way that you describe
effect handlers, I can hear. That's maybe we should take that offline, but it's a good.
Microsoft has something that does that. I think it's first time I have the name wrong.
No, it's not. It's in the Coca program.
It's in Coca does this, so at least it's polymorphic integration is really right. What data changes that does that dynamically? I was going to ask the obvious question, it's me, which is I obviously think it's very important, especially if you want to start building data abstractions, with not Scandinavian, I like to do it. Why don't I just have a nesting of regions? You need to trust now. So this region is inside this one.
Yeah, so the outlives relation, that's definitely, other people are working a lot on this thing, using kind of and this is different in the sense that it's based on unification of regions, but the other work will use a kind of an outlives relation where you say this region is alive at least as long as the other one, and so on. And then you can use those properties to kind of alleviate away from having to unify, and you get rid of certain other problems. So there are two different ways of, I think, of looking at. Maybe they can be combined. I don't know if that was.
Well, I think that. Well, I guess what I think is, I think there's a semantic issue of whether you're at some level you're dealing with flat regions or whether you're dealing with nested regions. And then I think there's an implementation issue, which again we find in standard type systems, DB type inference, and how sophisticated and how you do the unification. I think it's sort of doing something simpler. And I know, you know, in the ML tradition, you guys have done a lot of fantastic work in extracting the regional information out of programs where programmers didn't knew anything. And yeah, I guess the sort of other side has been a lot more explicit. We want to say, okay, this region containing these links is part of the region that is containing the object that is the links. And we'll rectify our messages you talked about here if you try and break that restriction. But then, you know, we can do what if we want to, we can do part stuff, and this was talked about, rather than talk about the allocation, because we know more about the structure of the regions the programmer is built.
I will leave it as a comment and not a question, but I think there's a lot of related work. I have not mentioned at all other people's work, but this is kind of the work mostly in what this is based on. In particular, the region inference algorithm by Toft and Birkedal, and also the unification and polymorphism in region inference. And then there's a lot of other slides, but I will just skip those for the sake of time. I think we took the question. If there are any questions, of course, you're welcome. I'm very interested in getting further with this stuff, but I think we have another speaker. I don't know. Yeah.